But we are doing general software development with an emphasis in artificial intelligence, machine learning, and deep learning for those around the valley that are interested in such things, or the wider world for that matter. And we also do a little bit of training in these areas. So if you have a software development staff, for instance, that needs to understand some of these tools better, we can help bring them up to speed. If you simply have questions in the area, we can answer those questions. And if you need work done in the area, but you recognize it's not necessarily going to be worth the while to bring someone on staff to do that, we can help with those types of things as well. I've been doing software development myself for about 20 years. Started in the web, moved on to the desktop, and then ended up in the cloud for a long time. I've worked in a whole bunch of different verticals, including telemarketing, finance. As of late, I've been in robotics and machine learning. I've spent about the last 10 years in those areas myself. I've worked at every level. I started with CSS and HTML, literally out of HTML for Dummies. Reading the text, deciding, do I understand what this is? Can I do this? Eventually got down to banging on microcontrollers and figuring out that, at that level you don't have a serial device, so you can't printf to debug. If you think printf debugging is a terrible way to put an LED into your circuit to figure out if your code is actually executable. I have a bachelor's in computing with a math minor, and then I have a master's in robotics and deep learning here with Yoshio and Goodfellow for the few here that might recognize those names. Point is, I've spent a lot of time studying artificial intelligence, specifically deep learning, which is a methodology that builds upon deep learning. Actually, I'll get into that in a moment, but if you've read anything about the last 10 years on machine learning or artificial intelligence, you're likely reading about these tools. I've also taught the artificial intelligence, machine learning, and deep learning classes at the university. And as of late, I'm co-organizing the Utah Deep Learning Meetup with I'm never getting his name right up. Thank you, Jared Haywood. Thanks for the help, John. I'm here because, in my mind, AI is sort of ripe for picking. We've had more than 50 years of research to figure out, this is way harder than we expected. When you go back to, there was an MIT summer project by Marvin Minsky, who's one of the grandfathers of the field, who decided he could solve computer vision in 3 months, and then figured out, no, we can't do that. But we've had a lot of advancement in those 60 years, and there are a lot of ways that AI can be used. We just saw, the CEO of HireVue telling us about how it's being used for interest research, right? That is not something that could have been done even 10 years ago at this point. Before we delve too deeply into the edge, I want to talk a little bit about what artificial intelligence is versus machine learning versus deep learning. AI is really the area of computer science that's looking at creating programs that are trying to solve problems with the capacity or capability of a human. So if I want to drive a car, I should be able to drive a car as well as a human, not Brett, for instance, right? Machine learning are a subset of such algorithms. So they're still artificial intelligent algorithms, but they have an added caveat. They are algorithms that have to learn from data. We want to give them data. Sometimes we want to give them the answer, and we want them to develop their own understanding of that data and give us back a prediction that we are interested in, and we guide them that way. And a lot of this is done at a very mathematical level. Deep learning is arguably a subset of machine learning, though in my mind lately they are becoming synonymous, one and one. And not just because most people are switching to them, but because actually at the mathematical level we can show the equivalences between the techniques a lot of the time, right? Classical machine learning techniques have some benefits in that they offer strong theoretical guarantees. If I want to predict something and I have some set of data, I can decide whether or not that data is going to predict this thing and how much of that data I might need. For instance, deep learning doesn't have these guarantees. A lot of the time when we build such a model, we don't know how much data we need. So we take a set of data, we apply it to the task, we measure its effectiveness, and then we may gather more data and try it again and see, and in all likelihood, we'll see an improvement in the accuracy on the task, right? Theory in deep learning is coming. In fact, I have a paper on deep learning theory myself, but there's just a lot to do, and the theorists are a little bit behind the empiricists in this particular field. Deep learning is a type of machine learning that I think of as learning on top of learning. So in classic machine learning techniques, you give an input, you say this is what the output should be, and it finds it's really an algorithm to map from the input to the prediction, right? But when we look at a text, what we do not do is see meaning. What we technically see are photons, right, to get very technical about it. It's the machinery of our body that compiles those photons into lines, those lines into letters, letters into words, words into sentences, paragraphs, chapters, etc. And at some level in that hierarchy, and likely a lot of those levels, we're extracting meaning, right? At least at the very word level. Even at the letter level, we can start to extract some kind of meaning. Some of our articles are just one or two letters. Why machine learning? Why deep learning? So this is really what I was getting at. We use data. We gather a set of data generated by some group of people that are performing a task we're interested in. We know how well they perform, and that can give us the extra juice, if you will, in our algorithms to solve these problems. Classic AI techniques were very logical, very mathematical, and often didn't perform as well because there were just missing pieces, right? Data helps us find that missing piece, if you will, a lot of times. Another interesting question is, why are these things happening now, right? The earliest thoughts on autonomy go back to Greek, right? With Plato and the like talking about autonomous figures, talking about bringing rocks to life, and these types of things, right? A lot of us in the AI will recognize that that's some of our humanity's first thoughts on AI. On intelligence, that's not us, if you will. But what's really powering us lately is data and compute. We've seen the internet come on board since the dawn of the computer science age, and that has brought us a great deal of data. It wasn't intended to, per se, it was intended to allow us access to the data that had already existed, and we expected it to generate more data, but it sort of generated head and shoulders more data than I think a lot of us had expected, seeing the inception of the internet come out, right? Compute, gamers. Interestingly enough, I consider myself a gamer. I haven't had a lot of time to do it as of late, but a lot of people told me when I was younger that is not a skill that's going to do you any good. Yeah, maybe not. We see hand-eye coordination is developed well through games, and analytical thinking skills can be developed through games. But in this particular case, gamers helped us by demanding more compute. So NVIDIA and the like started developing graphics cards that give us some more compute. And at some point, some machine learners figure out, oh, we can employ those devices to speed up our algorithms and actually make them effective, and that's where deep learning comes from. There's a lot of parallel computation that can be done. If you try to do it on a regular CPU, it's just simply going to take forever. But you throw it on a GPU because you can parallelize it, you get a lot of compute done really fast. So you're not speeding up the algorithmic complexity for those familiar with this idea, but you are speeding up the wall clock, the time required to actually calculate these things. I also attribute, as of at least the last 5 years, algorithmic improvement to be a major factor of why things are happening. This is not why the deep learning field or AI field in general has kicked off so heavily, but it is now the major area where people are making a lot of strides to improve its accuracy, right? And then as our previous presenter alluded to, data. Data is really one of the more complicated things to get a hold of, especially to get it without the biases that are going to cause the problems he was discussing, right? And being able to detect those biases and whatnot. Yeah. So ultimately, I guess I'm saying that I attribute data, compute, and algorithmic improvement as the reason we are seeing AI take off at this point in time. There are myriad ways in which we can use these technologies. Classic was image classification, sort of the story in our research field that gives credit to why all of this is happening is for a particular model called AlexNet that came out in 2012 to attack a problem called classification. They had a set of 1 million images. Each image had one of 1,000 objects in it, and the algorithm was tasked with looking at the image and deciding which object was in the image, right? Simple image classification. We moved well beyond that particular problem at this point into things like object detection. Now, not only do we want to know if there's, which object is in the image, we want to know which objects are in the image and where they're at. Please find the dog and box the dog so that we can see the dog. This isn't so interesting from necessarily a human's perspective, but when you get into like autonomous vehicles, they need to be able to see other vehicles, bikers, pedestrians, anything that can be causing them a problem, right? So not only do they need to know it's there, they need to know where it's at. Another interesting line of research in the vision world is style transfer. I take the Starry Night here on the top left, and I take this image of some buildings on the bottom left that I took while I was on vacation or whatever. I pass them to this model, and it renders my image in the style of that particular artist, right? So potentially less useful, but then you look at the use of Snapchat in these types of technologies, and you see that filters are used heavily for all kinds of different things. Another area is machine translation. You want that back up?
Yeah, thank you.
Yeah, no problem. So this is vision here, right? But we're also getting into text and audio with things like machine translation. We have models that can now take in a string of text from one language and spit out that same meaning to some level in 26 other languages simultaneously. We have chatbots popping up all over the internet. You go onto the website, you have questions. You're not finding it in the text. Perhaps you can ask somebody or something to narrow it down for you or give you a specific answer to your problem, right? Speech recognition, we've seen this around for a while. Siri, Google, Hey Google, these types of devices. You're really speaking to a deep model in all of these cases. We'll come back to these in a little bit. Other places where machine learning AI and the like show up is warehouse management. Some of you may already be aware that Amazon doesn't any longer have people in the warehouse that walk out to shelves and find your product and put it in a box and ship it to you. They stand at one position and the shelves drive to them. So the system decides your order includes this item. A robot runs out to that shelf, picks it up, brings it to the picker. The picker literally stands here, pulls the item off the shelf, puts it in a box, and doesn't have to move all day, right? And they're making great strides into eliminating that picker altogether. So you'll have a robot that will run out to the shelf, pick the item, put it in a box, and send it to you. That's where this type of device actually comes into play, sorting and packaging, right? It can sort of be that picker, though a lot of the solutions I'm thinking about in my head are they actually they'll go out and get the product. But this is the type of thing that the founder of iRobot got involved in to help small businesses. This particular device costs about 20 grand, and the idea is you can have a small distillery, or you can have someone doing Etsy stuff, maybe slightly on scale, having this thing help them package those items or whatever task can be done. Assembly is also another area where AI is used. Take a robot and say, here's an IKEA table, please put it together. This is very, very state-of-the-art work, not necessarily out there, but autonomous vehicles are pretty popular at this point. In fact, there are quite a few on the road. Every time I pass a Tesla, I always wonder, okay, is that one capable of autonomous, and is it running autonomous if it is? Most of their models for the last 10 years have been coming out with the right sensing suite, with the right sensor suite, but didn't have the software for a long time. Not too long ago, actually probably like 5 years ago, came out with a software update for their S-Class models, so you can push a button and it will start driving itself, right? We've seen problems from that, but we've also, people like it enough that they use it. I'm not sure if you guys have seen this little tiny little robot. Has anybody here encountered that by chance? So that is a delivery robot, right? The idea is that it will be in like a van or whatever. The van will drive up. Of course, it's autonomous ideally as well. It will drop this guy off. It'll run to the doors and drop the packages off, and then load back up in the vehicle and take it on. Some of the projects that we've been working on to highlight the reality of this scenario a little more involve swarm control. So a colleague of mine just finished his PhD on this work that we've been doing, wherein we look at how can a set of agents control another thing with minimal or no communication amongst those particular agents. So the example I like to think of is a plane, and really because this is the work we did, this is the model we used to work. The plane itself, you may not have control over. Imagine that its ailerons have gone out, and therefore you can no longer bankroll, pitch, or any of this, right? If you can attach a quad rotor to the wings, they can now control how that device moves by imparting force onto those wings, right? If one thrusts down heavily and the other one gets underneath and thrusts, you can cause the thing to pitch or roll in whatever direction you want to go, right? And we showed that this is completely possible. And the work we're doing right now is looking at how do you do it with zero communication amongst them. They all know what they need to do. They all know what the ultimate goal is for the object. Perhaps we're trying to steer this plane to a landing, but they can't communicate. Perhaps there's weather influencing the communication channels, or we're just not confident in the reliability of the communication channels, these types of things. Another project that I've done recently is that of animal tracking. One of my clients pointed out they're observing animals in the wild for the purposes of research, and they were using motion-sensitive cameras to do this. And everything from a gust of wind to the changing direction of the sun would cause activity that made the cameras think that it needed to record. So they would record, but largely the animals of interest weren't in the field of view, and they ended up with 10 times more data than they needed. So we went through and wrote a deep learning model that watches the video and then extracts out all these portions that actually have the animal in the scene, right? So they can now watch, they can have, at the time it was a research assistant who came to me and said, I have this ungodly number of hours of video to watch. I don't know that I can get it done in time. So we built this model. Now we can actually reasonably watch and catalog what those animals are doing. Another project I'm involved in is that of flying taxis, right? We're one of 50 remaining entrants out of 6,000 into an X Prize. It's $1 million purse for the company that can come up with the best design for a vehicle wherein you step into the vehicle, say I want to go perhaps downtown, I want to go to the Goldman Sachs building, and it will close up behind you, take off, land there, let you out. You don't have to have a pilot's license because you are not in fact piloting, it's piloting itself, right? This particular project isn't being done in isolation. There's another contest going on right now for building the best autonomous air traffic controller. So as I get in here and I want to say I want to go to Goldman Sachs, it's going to radio to an autonomous controller. The controller is going to say, please use this path, and we're going to follow that path, right? Nice and straightforward until, say, another vehicle dodges a bird and ends up in our terrain, or we simply need to dodge the bird. So some of the challenges we're dealing with are not only how do you vocally interact with the device and say I want to go to Goldman Sachs, but more importantly, how do you recognize that a mile off ahead of us there's a bird that potentially be a problem, and try to predict what that bird's going to do, and then try to plan around that without interfering in any of the other flight spaces around us, right? So that brings me to the edge. What is the edge? The edge is being defined as small compute, small memory, small power devices, right? And this is always sort of a nebulous term because with every passing year we get more and more capable small devices, right? And so the phone in my pocket currently is considered the edge, right? And will continue to do so. But the phone, that I can pick up in 2 years from now may not currently have the specs that we would consider the edge because it's going to be a lot more powerful, hypothetically, right? So really you just want to think about any device. The way I like to think about it is the device that's in the consumer's hands, which sort of allows for desktops to be on the edge, and in some sense they are. They're not in the cloud. But the point is we're not using the cloud for compute. We can get access to machines with very large amounts of memory and compute out there relative to what we can get in our hands sitting right here. And that is the edge, right? This is interesting because the number of edge devices over the next 10 years is expected to increase far faster than the number of, say, laptops and desktop computing devices that are out there, right? And so this opens the potential for us to use that compute, but it also shows us where people are going to be doing their computing. So if you have some application that you want to run on the phone, one of the examples I like to use is called Picture This. You take a picture of any plant that you find, and it will try to tell you what that plant is. It'll also try and go and diagnose the plant. Are you overwatering? Does it have an aphid problem? These types of things, right? This can run on the phone, or it can run in the cloud, and you can access it via the internet, right? Which is sort of a standard approach to doing machine learning with edge devices. That leads to problems, however. Specifically, it takes a lot longer for that kind of flight and for the computation to happen if you're using the cloud versus if you're using the edge device. Now you have the opposite problem with edge devices. Again, we're talking about low power, low memory devices. So fitting these models on there and getting the computation done efficiently can itself be a problem. And that brings us to the sort of libraries and hardware I want to talk about. Right? There are a lot of libraries out there that are focusing now on doing machine learning and deep learning on the edge. TensorFlow Lite, TensorFlow itself can be ported. Well, TensorFlow itself can actually be ported to a lot of microcontrollers. You really run into memory issues at that point, and TensorFlow Lite is a sort of an answer to that. How do we take the most popular operators in the library and make them available on these devices, and can we do it such that the compute takes advantage of the device itself and is sped up in some way? Right? Core ML, the top right icon there, is another solution that's out there. It's offered by Apple, so you can take, say, your Keras model or whatever you happen to be developing in, and port it over to iOS devices pretty straightforwardly. In fact, one of my colleagues has a couple of blog posts he's built where he shows you can take a model you have trained and put it on your device in under 5 minutes. Right? Pretty straightforward. Microtensor is the other one that recently entered my field, which is really interesting. It takes a it supports TensorFlow in full, but sort of tries to do what TensorFlow Lite does while putting more under the hood so you're not having to deal with a lot of technical detail. It is, on the other hand, targeting even smaller devices. We're talking sub-meg memory devices. Right? So perhaps I want to have an audio security system on my door at home. Right? I don't want to give my kids the key. I don't expect that they will do well at retaining that key, but I want to offer them a way to get in my house very easily. I don't need anything other than to be able to authorize them through their voice, right? And with these very tiny devices, in fact, I've got one that's coming up. I'll just wait until we get to that. Some of the devices that are available are Intel's Neural Compute Stick. This came out, I want to say, about 2014. One of the earliest that I know of in this area. You plug it into your computer, and it offloads the computations related to your model to this device. And this device has been optimized for those computations. So you get your data, you get your model, you push your model onto this device, and then as you stream data through it, it takes the data, processes using that to answer fairly rapidly, right? Similarly, NVIDIA, more recently, in the last couple of years, has come out with the Jetson. Now, they've had another device that is, the name now is escaping me. I want to say it's in the Jetson series for the last 5 years or so. Not really intended to do machine learning and deep learning, more targeted for robotics. And this has a lot of influence on robotics as well. But this is sort of blending the worlds of artificial intelligence and robotics. Another interesting one is the I didn't read the label there, but excuse me, the Javois smart machine. I picked this particular image because of the quarters, right? Because the change there gives you a sense of how big it is, but it actually runs TensorFlow. Build yourself a convolutional neural network to do image recognition or object detection or whatnot, and you can port it to this device. So imagine carrying this around on your lapel or whatever. Excuse me. Oh, I lost this slide. My apologies. So the one I was talking about before is the SparkFun Edge Development Port. This thing is also about the size of a quarter, and will do things like audio recognition, or you can perform like weather analysis, what's the temperature, how much rain is happening, these types of things, right on this tiny little device. So long as your model doesn't require a lot of compute, the SparkFun Edge Development Port is really good. And then what I have here with me today is Google's Coral, and this is sort of what got me excited. I initially jumped in with my consultancy firm to help people understand the research is still very bleeding edge, but there's a lot of the research that's ready for us to actually make products with and make them, improve the consumers' lives. And then fast forward a few months, and Google announces this board. And as soon as I saw it, literally as soon as I saw it, I went and ordered it, right? Very fun little machine. Is anybody here familiar with Raspberry Pi? I'm going to go, a lot of hands will show up. Okay. So Raspberry Pi is a small computer on the same order size of this. In fact, it's the same shape. And it was originally intended for making compute available to kids so that they can learn programming or browse the internet or whatever they need to do in school on the charge of around $25. Very, very cheap but very capable computer nonetheless. This is in that same arena. It's a little more expensive, but it has hardware built specifically for doing the computations that you do in machine learning and deep learning, right? So the speeds goes up heavily. In fact, this particular board, while a Raspberry Pi can run independently as a computer, display on a monitor and take keyboard and mouse input, this one can, but it's not intended to do so because because you want to use all of its resources as best you can for the machine learning that you're going to be performing. So it's usually intended to run side by side with another computer somewhere around. And that brings me to the teachable demo that I wanted to show up. How much time? I'm more or less out of time, so I might have to show this after the fact. But let's see if we can. Let's just see if we can do a couple real quick here. So the point of this is to show off that this is an edge device, very low capabilities. It's got a gig of memory, 4 gigs of hard drive space, and then a Cortex M4 on the device, right? So I don't want to say it's 4 cores. I'm not completely certain. That might be 8, but I'm pretty certain it's 4. And we're going to perform a couple of machine learning tasks on it, if I can think about which ones they are. So recently I've been looking at, so you can port your own models to this thing, and a lot of these commands are related to that. We're just going to skip that. We're just going to go right to the teachable demo. Or teachable machine, that is teachable. Now, apologies. To a live demo, right? Since I executed this, so I have not remembered. Okay, so in this case, what it's going to do is set all the version I'm through. It's going to start telling us what it sees, right? And it's going to tell us that via a number that is very small. Go back. can you see that better?
Yeah.
Okay. So in running this, we see 2 dashes on the right there, and that's telling us what class it sees. And all it's telling us is that it doesn't see anything at the moment, right? And if we show it anything, as far as it's concerned, it looks like everything. So we're just going to say, we're going to take a bunch of pictures right now. I'm sitting here pushing the 1 key, and every time I do that, it tells it to take a picture. And what I'm doing is I'm training it to recognize the world, right? What does the world look like right now? And of course, it still looks like itself. No matter what I do to it, it's not going to see the world as being different, even though it is. Because there's really nothing to compare to. But now if I say, let's see this device in our world. If I take this away, it sees the world, right, as we showed it. But if I bring this into place, it now recognizes that this is there versus when it's not there, right? Similarly, if we take it and show it another thing, take a bunch of pictures, give it different angles, so it can recognize it from those angles. And if we take this away, so you can differentiate between these objects, right? Now, it turns out the particular approach they're using here is very easy to fool, right? In fact, can we just do it by bringing this up? Yeah, see? Now, and really what's happening here is you can discern that it thinks this is this because I've made this in its field of view sufficiently smaller, and it starts downweighting the head on this thing, right? So it is by no means bulletproof, and this is one of the things that our previous speaker was talking about, recognizing what bias is, where it's coming from, what features are good for performing what task, that type of stuff. This one will be a little bit easier for it to recognize because it's so distinctly different from the other. But in all these cases, it's still, as long as the object is in the right area, this is a good tricky one to play with. This is where we have a lot of work to do. That is what I wanted to show you today. Any questions? Please.
The Google, who was it, Facebook that did the deep learning that beat the Go game, Go Professional? Do you have any thoughts on that? Because I thought that was kind of interesting.
It is really interesting. I guess the immediate thoughts that come to mind are this is an attempt by our community to push the problems out of the toy world. Autonomous vehicles are also obviously an application of that, but AI, when it first got started, and I'm sort of surprised that Mariah didn't jump out in the beginning of my talk and argue with my Venn diagram again. You're good.
You made some good points that I appreciated.
No, but that's the point. That's what you're asking for is AI, when it first started, was a field of research to sort of replace us in tasks. And when we started doing the research, we realized, oh my God, this is really hard. What are we going to do? Well, we're going to simplify the problem. We're going to attack it, and then we're going to complicate the problem and attack it. And over 50 years, AI has now become this field of research that attacks a toy problem, or a small problem, individual problem. And really, we want to go back to those roots of developing an AI that can do all the things we can do. And now we coin the phrase artificial general intelligence, right? And so the Go development is a way to show we can increase the capacity of these things to do more than one task, and not just simple tasks, very complicated tasks. Try and get towards AGI, right? Once again, we'll always sort of be striving for that. But there's a lot to be said on the technical side too. If you have any particular questions there, I have given entire hour-long talks on just those techniques alone. So, is there any particular you want to know about?
Just general thoughts that you might have.
Yeah. So, first thing that comes to mind is that it's an approach to it's an attempt to get us closer to AGI. Anybody else?
Regarding AI and sound,
Yeah.
is this device capable to recognize that as well?
Yeah. So this device is pin-to-pin compatible with a Raspberry Pi, and a Raspberry Pi has a 32-pin GPIO output for attaching sensors and the like to, and one of those sensors can certainly be a microphone. In fact, this, I believe, is a microphone input right here, so you don't even need to go through that part. Just attach to a standard 3 millimeter up here.
I got a question just about the hardware of Google World. Like,
Yeah.
I know Raspberry Pi is like the ARM-based processor as well, but then like the NVIDIA Jetson has like GPU, way more GPU compute power. Does Google World have more GPUs than Pi?
Yeah. So Google developed a chip they called the TPU, the tensor processing unit. Tensors are the sort of elemental mathematical structure that we use in deep learning machine learning. Right? And so this thing was optimized to perform those. And it's housed in servers in their cloud. Right? This product, with this, they decided to take that chip and make it much smaller. It's much less capable as a result, but it's also much smaller so that it can fit into a package like this and still speed up those same computations. So it's not a GPU. In a lot of ways, it's better than a GPU because these particular, when you embed an algorithm into silicon, you get less power requirement and optimized speed, right? And a GPU is somewhere between this type of circuit and the classic quantum architecture CPU, right? So this cuts the middle, or rather, a GPU cuts the middle between what this can do and what the CPU can do, right? Sure.
Dustin, do you have any thoughts about Firebase ML?
Not right off the top of my head, no. Sorry. Anybody else?
Come on.
Come on. You can give us yours. I always like to hear your thoughts.
Firebase?
Yeah. Is it any good?
From what I understand about Firebase ML is it's an attempt to apply the AutoML technique to data sets. So it's very similar to any kind of, let me just put it this way, there's lots of machine learning processes that can be run on data pipelining or data storage options. Most data warehouses are adding ML techniques. Spark has them, Hadoop has them. So basically, any kind of classification, general processing, labeling things are being done as part of your database storage structure or a data transformation layer. And they're just very trivial at this point. So everybody does it, so they're very trivial operations and easy to implement at that layer. So I would trust it. I haven't used it, but just because of how trivial they are in nature, I wouldn't trust it.
I'd have to look into it to tell you. I'm not particularly familiar with that one. I tend to go to GCP myself. A lot of my clients are small enough. They're in a position where they can't hire. They either can't or don't have the resources or the time to hire people dedicated, right? Especially to IT. So they tend to go to the cloud. All right. Please feel free. I'm going to be here all day, so please feel free to talk to me. Taking out anybody I see that's interested in myself, I'm not shy. Thank you all.